Welcome back to the magic that is geometry. Today, we're going to talk about reasoning in algebra and geometry. Let's do it. So maybe you thought since the class is called geometry, you get a free pass and you don't have to remember any algebra. Not so. Here are some things that we have to remember from algebra. Now these are properties for real numbers. And you used a lot of these when you were learning how to solve equations. Like the addition property of equality says you can add the same number to both sides of an equation. Subtraction property of equality says you can subtract the same number from both sides of equations. Multiplication and division property, you pretty much get that. You just can't divide by 0. The reflexive property was one that you probably were introduced to and then never really thought about again, that some number is equal to itself, because that's pretty obvious. Symmetric property, if A equals B, then B equals A, also pretty obvious. Transitive property, if A equals B and B equals C, then A equals C. And the substitution property, if A equals B, then B can replace A in any expression. These three fellas right here are kind of highlighted there because they have corresponding properties that are true for congruent figures. So we got to remember, if we're talking about numbers, then we're going to be talking about the property as it relates to equality. If we're talking about congruent figures, which we will later on, we're going to talk about the reflexive property of congruence. The old distributive property. We go way back. You remember the distributive property, don't you? You love it. Basically, if you got some number multiplied by a sum or by a difference, you can just multiply that number by each term inside that sum or difference. And if it's plus, then they're both plus, and if it's minus, then the minus goes with the term that was negative. Alright, so let's take a look at a practice problem here. So in geometry, we deal with logic a lot and proofs, and so there's a big emphasis on justifying each step. So let's take a look at this problem. What's the value of x? Well, what do we know about this picture? What do we know about this picture? Well, we got line AC, and then we got ray OM coming off of that. And it looks like that these two angles are a linear pair because they stick together to make a line. So we can say that angle AOM and angle MOC are supplementary because angles that form a linear pair are supplementary. So that means that the measure of angle AOM plus the measure of angle MOC is 180. Now I want you to notice the difference between these notations. This notation is talking about the angle itself, the two rays with the common endpoint. We're talking about an angle when we see this. So this is talking about a geometric figure. When we put the little m in front, now this is the measure of angle AOM. This is a number. This is no longer a figure over here. We're talking about the value that represents the size of that angle. So the measure of AOM plus the measure of MOC is 180. These are two numbers that we're adding together. And we can say that because that's what the definition of a supplementary angle is. It's two angles that add up to 180 degrees. So then what can we do next? Well, we can use the substitution property because right here we're told what the measure of angle AOM is, and right here we're told what the measure of angle MOC is. So we can substitute this expression for measure of angle AOM, and we can substitute x for the measure of MOC. So I'll do that right now. 2 times x plus 15 plus the measure of angle MOC is x. And then now we're going to start using those algebraic properties that we know so well. We'll use the distributive property. 2 times x plus 2 times 15 is 30. Then we're going to use the subtraction property of equality, and I'll add in there, we're going to combine like terms also. We're going to subtract 30 from both sides of the equation, and then I'm going to combine these like terms too. 2x plus x is 3x, and 180 minus 30 is 150. Now, we're very close to having x all by itself, but x is currently being multiplied by 3. So what's the opposite of multiplying by 3? Dividing by 3. So I'm going to use the division property of equality to divide both sides of the equation by 3, and then I get x equals 50. That was pretty cool, huh? I liked it. So go ahead and pause the video and see if you can figure out this one. It looks like bran. So think about cereal while you're doing this question, and then push play when you're ready to see me work it out. Okay, so we are given that ray AB bisects angle RAN. All right. So what does that mean? You may recall that the definition of an angle bisector is this ray or segment that divides an angle into two congruent angles. So we know that angle RAB is congruent to angle BAN. And congruent angles have the same measure. So we know that the measure of angle RAB equals the measure of angle BAN. Notice the notation here. When I'm talking about angles, I say that the angles are congruent. When I'm talking about their measures, which are numbers, I say that those numbers are equal. So what did we use here? Here we used the definition of an angle bisector. Here I'm justifying my steps. And here I used the definition of congruent angles. Okay, what's next? Well, I can use the substitution property. Because I know that the measure of angle RAB is x, and I know that the measure of BAN is 2x minus 75. And now I can use the, let's see, I have x's over here and I have x's over there. Well, I got 1x over here and 2x's over there. So I'd like to get my x's on one side and some numbers on the other side. If I was to subtract by using the subtraction property of equality, and if I was to subtract x from both sides, what would I get? Is it a mystery? 2x minus x is x, and I would still have minus 75. And what do I have over here? Nothing? If I have x and I take away x, I have nothing. And what's nothing in math? 0. Ooh, I'm very close, I'm very close. I just need to add 75 to both sides using the addition property of equality. So then I get 75 equals x. And then I'm happy because I have x by itself and I know what number it equals, so I'm happy. Because that's what they wanted me to do. They wanted me to find the value of x. And I did it. So there, math problem. You just got socked in the face. Violence isn't the answer, though. Okay. This is where algebra and geometry come together. And hopefully we have a parent present. At least one. So there's no fighting. So the reflexive property of congruence. Remember, the reflexive property of equality was that a number a equals itself. Remember, it was a equals a. So now we're going to say, now we're talking about geometric figures with congruence here, and we're saying, so like a segment is congruent to itself. An angle is congruent to itself. So any figure you have is congruent to itself, right? Just as obvious as a number is equal to itself. The symmetric property. If segment AB is congruent to segment CD, why then segment CD is congruent to segment AB. Also obvious. Remember, for numbers, it was if A equals B, then B equals A, right? Not blowing anybody's mind here. But these are just kind of basic things that when we're justifying everything like we do in geometry, we justify everything, we got to start at the very basic stuff, like, yes, if A equals B, then B equals A. Yes. If the segment AB is congruent to segment CD, then of course segment CD is congruent to segment AB. Same thing with angles. If angle B is congruent to angle A, I said it backwards, then angle A is congruent to angle B. And then transitive property for algebra was if A equals B and B equals C, then A equals C. So it'll be similar with figures. If AB is congruent, if segment AB is congruent to segment CD, and segment CD is congruent to segment EF, then segment AB is congruent to segment EF. Same thing with any kind of angles you want to talk about. Okay, let's do a problem. Problem 2. What is the name of the property of equality or congruence? So remember, equality is for numbers, and congruence is for geometric figures. So what is the property of equality or congruence that justifies going from the first statement to the second statement? So here we got 2x plus 9 equals 19, and then our second statement is 2x equals 10. Well, how on earth did we get from 2x plus 9 to 2x? I think we might have subtracted 9. Well, let's see. If we used the subtraction property of equality, that would mean we have to subtract 9 from both sides. Does that give us... oh my goodness, it totally works. So that was the subtraction property of equality. All right, here's some Harry Potter angles for you. Angle O is congruent to angle W, and angle W is congruent to angle L. Thus, we conclude that angle O is congruent to angle L. What property did we use? We used the transitive property of congruence. All right, how about this guy? If the measure of angle E equals the measure of angle T, then the measure of angle T equals the measure of angle E. Now this is the symmetric property. If this equals that, then that equals this. But are we talking about geometric figures, or are we talking about numbers? Is this the symmetric property of congruence, or is this the symmetric property of equality? And the trick is, here's a little hint right here, there's an equal sign, not a congruent sign. The measure of angle E is a number. The measure of angle T is a number. And numbers can be equal to each other. So this is the symmetric property of equality. Alright, pause the video. See if you can do got it number 2. And then push play when you're ready to see how smart you were. Alright, here we are. Segment AR is congruent to segment TY. And then our second statement is segment TY is congruent to segment AR. Well, this is symmetric because we're going one way and then we're just going the other way. But since we're talking about a segment being congruent to a segment, this is the symmetric property. I'm going to write very horribly here. The symmetric property of congruence. B. 3 times the sum of x and 5 equals 9. Second step, 3x plus 15 equals 9. Well, that is what we like to call the distributive property of awesomeness. And then how would we possibly get from 1/4 x equals 7 to x equals 28? Well, one way we could get there is by multiplying both sides by 4. 4 times a fourth is just 1, so that's 1x. 7 times 4 is 28. So this was the multiplication property of equality, because we're doing numbers here. All right, reasoning. What property justifies the statement measure of angle R equals measure of angle R? Well, that's a reflexive property. I think about it as like looking in the mirror, reflecting the measure of angle R is equal to itself. But are we talking about numbers or talking about a geometric figure here? And measure of angle R is a number equal to a number. So this is the reflexive property of equality. And you may have thought you just heard like a pteranodon screaming in the background, but no, that was just my children. And the secret phrase for this lesson is humdinger. All right, now in geometry, we're going to do a lot of proof. Proof is a convincing argument that uses deductive reasoning. It logically shows why something is true. A common way to write a proof is this 2-column proof method. You've probably seen it before in algebra where we write a step on the left and then we write the justification on the right. And in geometry, we just use that to, instead of doing a math problem, we just follow a logical argument. So a two-step proof or a 2-column proof kind of looks like thus. You're given something, you're always given something. You always got to start with something. And then you have a goal. So this is where you start, and this is your goal. And here's a little cool trick. If there's ever a multiple choice question with fill in the blanks on a proof, the first thing is always going to be the given statement. And then the first reason is always going to be given. The last statement is always going to be the thing you're supposed to prove. All right, but what goes in between? What goes in between? Well, the first statement is usually the given statement. And by usually, that means pretty much always. Then in between, what we need to do is we need to say, all right, here's what I know. What am I allowed to conclude based on that? That's what we've been doing the last couple lessons. We've been given some statement, and then we've been trying to figure out what logical conclusion can I make from that. And then we just do that step by step until we get to our goal, which is always what we want to prove. So this is always going to be the last statement. This is always going to be the first statement. And then the first reason is always going to be given, because we were given that. All right, let's see a 2-column proof in action. We are given that the measure of angle 1 is equal to the measure of angle 3. We need to prove that the measure of angle AEC is congruent to the measure of angle DEB. All right. We know that the measure of angle 1 is equal to the measure of angle 3. We need to prove that the measure of angle AEC is equal to the measure of angle DEB. So what's the plan? The plan would be add the measure of angle 2 to each one of these. Angle 1 plus angle 2 should be equal to the measure of angle 3 plus measure of angle 2. All right, so that's our plan. Now let's follow the plan. Remember, what do we always start with? The given statement. So we're given the measure of angle 1 is equal to the measure of angle 3. Now, from that information, what can we say? What's our next thing that we can say? Well, we know by the reflexive property of equality, because remember, measure of angle 2 is a number now, the measure of angle 2 is equal to itself. according to the reflexive property of equality. So now I have, so why did I say that? Measure of angle 1 is a number, and I have it equal to another number. And if I want to be able to add two numbers together, say I want to do measure of angle 1 plus measure of angle 2 is equal to measure of angle 3 plus measure of angle 2, these all have to be numbers. And so I have to have stated at some point that these two numbers are equal. Because look what I'm going to do next. Now I'm going to say measure of angle 1 plus measure of angle 2 is equal to the measure of angle 3 plus the measure of angle 2. Why am I allowed to say that? Because right here I said that the measure of angle 2 is equal to measure of angle 2, and I'm allowed to add the same number to both sides of an equation. It's kind of trippy that these are just numbers, right? They're not actually like geometric figures. I'm just adding two numbers over here and I'm adding two numbers over there. And I'm using the addition property of equality because I'm dealing with numbers here. So here I have one sum that's equal to another sum. Okay, but think about what measure of angle 1 plus measure of angle 2 is. Measure of angle 1 plus the measure of angle 2 is the measure of angle AEC. Right? Do you remember what postulate tells us that? That's right, it's the angle addition postulate. Well done. I'm glad you said that out loud so that I could hear you. Alright, so by the angle addition postulate we can also say that the measure of angle 3 plus the measure of angle 2 is the measure of angle DEB. Okay, so we're getting to the bottom of the page here, so we should be getting close to this, right? Well, let's see. If I was to use, let's see, what is this right here? This is just the measure of angle AEC. If there was only some property that I could use to just substitute this notation for this sum. Wait a minute, there is such a property. It is called the substitution property. Since the measure of angle AEC is equal to this sum, I can substitute it in there. And since the measure of DEB is equal to this sum, I can substitute it in there. So now I have the measure of AEC is equal to the measure of angle DEB. I have taken what I was given, I have followed a bunch of logical steps using properties and postulates that I know from the past, and I got to my goal. Winner, winner, chicken dinner. You might see this on the occasional proof. This was old school. When you're done with the proof, you say, you say QED. And that's like, truthfully, I think that's Latin for like quo eras demonstrata, something like that, which means it has been demonstrated. But a lot of mathematicians like to say quite easily done. So QED, my friend. Wahaha! Ooh, can you do this? Pause it, do your best, and then push play when you want to see how awesome you are because you did it right. Okay, so we are given that segment AB is congruent to segment CD. And we are given the goal, the task, nay, the opportunity, to prove that segment AC is congruent to segment BD. Now, we're going to use kind of a similar method that we did with the angles. Remember, we'd use the angle addition postulate. Here we're going to use the segment addition postulate. So, what can we say? What should we say first? Well, a good place to start is our given statement. So how about this? Segment AB is congruent to segment CD. I like it. I think that's a good place to start. Okay, well, what good does that do me? Where can I go from here? Well, when you're trying to decide where to go on a proof, it's good to come back to your plan. Remember, my plan is to eventually, I want to be able to say, I need to say that AC is congruent to BD, right? But I need to use the segment addition postulate. But the segment addition postulate is talking about if I add the length of segment AB to the length of segment BC, then that gives me the length of segment AC. And that's numbers. So I need to be talking about numbers instead of just geometric figures. So I need to make the transition from geometric figures and congruence to numbers and equality. So let's turn this into numbers. I can say now that the length of segment AB is equal to the length of segment CD. Those are numbers. I can say they're equal. Why can I say that? Why can I say that? Because that is the definition of congruent segments. They have the same measure. Okay, so now I have this number equal to this number. What else do I need to say? Well, I got this is my missing link, this BC business. Well, what do I know about BC? Well, using the reflexive property of congruence, I can say that segment BC is congruent to itself. And that's an ugly 3. Sorry about that. And now I can say that the measure of segment BC is equal to the measure of segment BC, and that is same reason as reason 2. Definition of congruent segments, same measure. Alright, what is next? Okay, so I've got some numbers. I got the length of AB is equal to the length of CD. And I've got that the length of BC is equal to the length of BC. So, if I was to add the length of BC to both sides of this, so I'm going to say length of AB plus length of BC is equal to the length of CD plus length of BC. I'm allowed to do that because I'm adding the same number to both sides of an equation, and that is the addition property of equality. What is next? What is next? Well, look at segment AB and segment BC. They're collinear and they share the endpoint B, so I can use what I like to call the segment addition postulate to say that AB plus BC, so the length of segment AB plus the length of segment BC equals the length of segment AC. And by that very same segment addition postulate, I can say that the length of CD plus the length of BC equals, okay, now look up here, CD, length of CD plus length of BC equals the length of BD. So you see me getting closer to my goal here. I have right now, I'm very close to being able to say that AC is congruent to BD. It's kind of fun. So here's what we have. We've got the length of AB plus BC is equal to AC. And we've got CD plus BC is equal to BD. And since these two were already equal, we can use the substitution property of equality to say that the length of AC is equal to the length of BD. Right? I'm just substituting AC into this side of the equation and substituting BD into this side of the equation. Well, now I'm super close, because what is the definition of congruent segments? Remember up here, they have the same measure. So by the definition of congruent segments, I can now say that since these have equal measure, I can now say that segment AC is congruent to segment BD. QED. Now, I might recommend that you rewind and walk through this proof a couple times. Make sure you understand every step because you're going to need to be able to write these proofs on your own, given, different given information. All right, and you're going to get some practice doing that on practice 2.5 and formal write-up 2.5. And I will see you later.